Good morning, students. Pustis are back again after some gap. I think you must be feeling what happened to sir. Don't worry, I'm back again due to some personal issues. I was slightly away from my lecture. Now let us start with renewed vigor. Today I'm giving you a very theoretical discussion. Delay neutrons making the nuclear power generation possible. This comes under your nuclear physics topic. Before that, my credentials you might have forgotten. This I have written here, and you must be aware now. All of you must be aware of the fission-based power plant generating clean power. Clean power, when I say there is no emission of toxic gases into the environment. So let's get into a bit details of it. Normally, our fuel for nuclear power generation is uranium-235, as it is more fissionable compared to other isotopes of uranium. आपको ये मालूम होगा, डेफिनेटली ये जानकारी होगी आपको कि जो 235 uranium 92 है, 92 is the atomic number, 235 is the mass number. ये ज्यादा फिशनेबल है, जैसे कि 238 इजीली फिशनेबल नहीं, नॉर्मली फिशनेबल नहीं. सो आज थर्मलाइज्ड न्यूट्रॉन, आज ये थर्मलाइज्ड न्यूट्रॉन मीन्स क्या है बाबू? तो न्यूट्रॉन का काइनेटिक एनर्जी ऑलमोस्ट 0.04 EV होता है. मतलब एट द रूम टेम्परेचर व्हाट एवर द एनर्जी as per the Boltzmann statistic 3/2 kT, जो भी एनर्जी है, so that energy neutron are known as thermalized neutron. The thermalized neutrons normally get absorbed easily rather than the fast neutrons. So as a thermalized neutron gets absorbed by uranium-235, it converts to uranium-236. Star means it's a higher energy state. 236 uranium-92, higher, all the nucleus are their unique energy levels like atoms. So it is in a higher energy state. Having excitation energy, E excitation energy exceeding the activation energy. Activation energy means what? Energy required to cause a fission producing fission. Okay. On an average, 16% of this excited 236 U92 nuclei undergo fission. सारे कुछ नहीं होगा. It's a case of probability. Even if they are fissionable, the activation, the excitation energy is more than the activation energy. But all of them don't get undergo fission. On an average, 16% of this excited U236 undergo fission. Producing what they produce? Fission means breaking into two smaller daughter nuclei. So, in general, the daughter nuclei which are produced from 236 uranium to uranium-92, they are of unequal sizes, unequal mass numbers. Because having just equal mass number, the probability is very, very low. So all these daughter nuclei which they get formed they have higher binding energy per nucleon than the parent nucleus of uranium-236. This fission process also release more than one neutron. More than one neutron they produce. When they produce this more than one neutron, practically at the instant of the fission. These neutrons do possess average kinetic energy almost 2 MeV. This is the average one. It may range between the hundreds of keV to maybe 10 MeV also, but the average is 2 MeV. These are called prompt neutrons because they are produced promptly, immediately at the time of fission itself. They are fast neutrons also because having 2 MeV kinetic energy makes them fast, qualified to be called as fast neutrons. Understood this? So the fast fission product will be the first daughter nucleus. Also undergoes the daughter nuclei, which are there formed after the immediately after fission. Their N/P ratio will be similar to the parent nucleus of uranium-236, but the N/P ratio for a lower mass number nucleus should be less than the 1.57, which is the N/P ratio of uranium-235. Okay, so to bring the N/P ratio commensurate with the respective mass numbers, beta decays, negative beta decays do take place. Okay, that you must be knowing. So that finally the daughter nucleus, which are immediately formed, they also undergo a series of beta decays to finally achieve a stable configuration, to arrive at a stable product. So these daughter nucleus which are immediately formed, they don't remain for a long time. They also undergo a series of beta decays to attain a N/P ratio commensurate with their respective mass numbers. Okay. So the generation time of these above neutrons, okay, this neutron which are produced immediately after the fission, yes, that generation time of these above neutrons are almost identical to generation of daughter nucleus. So this is the just the time taken for the fission to happen. That is almost a fraction of picoseconds, as you see from this. That's why these are known as prompt neutrons. Immediately after the fission, these neutrons are produced. More than one source. Let's take a typical fission reaction, which is not the only one. There is so many products can be formed. There is not a unique pairs possible. So this is one formalized neutron get absorbed into uranium-235, becomes uranium-236 star, then break into cesium and rubidium, and 3 neutrons. A typical one, sometimes 2 also. The number of possible fission products are very large. That's what I told. It's not only cesium, rubidium, there's so many other krypton and all this. After the emission of the prompt neutrons, usually there is no direct emission of neutrons anymore. कोई डायरेक्ट न्यूट्रॉन होता नहीं उसके बाद. तो आप बोलेंगे भाई प्रॉम न्यूट्रॉन तो सारे हो गए, फिर अब डायरेक्ट न्यूट्रॉन है नहीं, तो फिर देन डिले न्यूट्रॉन की क्या बात हो रही है. चलो देख लेते हैं. However, in some cases, the fast daughter nucleus, जैसे कि first daughter after the fission is 87Br35, उसका daughter after a beta decay is krypton 87 krypton. So first daughter's daughter. So that's what I'm saying. The first daughter nucleus formed after a negative beta decay has excitation energy higher than the neutron separation energy. ये जो फॉर्म हुआ क्रिप्टन फ्रॉम द daughter is krypton, उसका जो एक्साइटेशन, सम ऑफ देम आर एक्साइटेड स्टेट स्टार, यू कैन सी 87 krypton 36 ground, 87 krypton 36 excited. E almost 99.97%, E 0.037, 03, maybe I call it as 0.03%. Okay, this is the higher energy state krypton. इसका जो एक्साइटेशन एनर्जी है, the higher energy state krypton is more than the neutron separation energy. So a neutron simply comes out from the, while the daughter's daughter is formed, and from the daughter's daughter, the one more neutron comes out, because the daughter's daughter has a excitation energy more than the neutron emission energy. That is which is more than the energy required to emit a neutron. After that, they all go for the other products by normal beta decay, and no further neutron comes out anywhere. They proceed till downstream till they attain a stable N by P ratio, the optimum N by P ratio. Okay, so daughter nuclide formed after uranium-235 is the Br87 Br35. From there, the daughter's daughter again formed after a half-life of 56 seconds. That is, krypton forms, and krypton has 99.97% krypton will be in ground state, will undergo again normal beta decay, but 0.03% krypton is excited state, where it is the excitation energy more than the neutron emission energy. So that there is a distinct probability of some neutron coming out, and they do come out. We call them delayed neutron. Okay, mark my words, it's all probability, I'm telling you. Similarly, second example, लेता हूँ, और एक daughter product है coming out of uranium-235 fission, rubidium 93, 6 second half life है, इसका कितना half life था? 56 second था, इसका कितना है? 6 second. तो बीटा डीके के बाद daughter's daughter strontium is formed. 98.6% normal strontium ground state, but 1.4% strontium is formed in higher energy state, and whose excitation energy is more than the neutron emission energy. So there is a distinct probability of neutron being released. So that is known as delayed neutron. So these neutrons which are getting produced, they are not prompt neutrons. Prompt neutrons has already been produced at this point when the fission has taken place from uranium of the uranium-235 or uranium-236 nucleus. That fission time itself, the prompt neutrons are produced, and they are fast neutrons as well. And these neutrons which are produced from daughter's daughter, they are also almost fast neutron, only less fast than the prompt neutrons, but fast neutrons nevertheless. And but they are produced after, what is the production time of the fast neutrons? Almost picosecond, immediately during the fission time. But here the delay neutron is formed from daughter's daughter. So the average time for producing a delay neutron is half-life of Br2 square, that is 56 seconds. Half-life of delay neutron from rubidium to strontium is the time, average time to produce the delayed neutron in case of rubidium to strontium transformation is the half-life of rubidium to strontium transformation, that is 6 seconds. So like this, so many daughter products are produced that we take an average of all those cases, all those reactions, and they give the first daughter to daughter those average time. If we consider this will be for uranium, it is almost 14 seconds. Okay, for the delayed neutron. This will be 14 seconds. We'll see that later. And the total number of neutrons emitted in the fission is how much percent? Here percent I gave 0.03% here. Here it is 1.4%. Similarly, so many pairs will be there. So many pairs are formed. This is one of the first pair. This is one of the second pair. This similarly so many pairs, and if we take all the pairs and we calculate the fraction of delayed neutron of the total number of neutrons emitted, for uranium-235 it is 0.64%. For plutonium it is 0.21%, like this. These are data. Don't worry about it. So आप बोलेंगे चलो ठीक है, तो फर्स्ट न्यूट्रॉन्स तो प्रोड्यूस हो गए, प्रॉम्प्ट न्यूट्रॉन्स तो प्रोड्यूस हो गए ड्यूरिंग द fission itself, and delayed neutrons are produced after a time delay equal to the half-life of the first daughter's transformation. The daughters, they are produced from daughter's daughter. So to produce the daughter's daughter, the time average is 56 seconds somewhere, in some cases 6 seconds, some cases it is 25 seconds also. So on an average, I have written later, that is 14 seconds, and the fraction of delayed neutrons of the total number of neutrons is 0.64% for uranium-235. चलो ये बात खत्म हो गई. अभी डिलेड न्यूट्रॉन समझ में आ गया. फ्रॉम न्यूट्रॉन्स तो आपको मालूम है, फटाफट निकल जाते हैं फिशन के साथ साथ, एक पिको सेकेंड ड्यूरेशन, काफी हाई एनर्जी रहता है. ऑलमोस्ट एवरेज एनर्जी आप लेंगे तो 2 MeV तक रहता है, एवरेज वैल्यू 2 MeV रहता है. तो इंडिविजुअली दे मे गो अप टू 10 MeV also. And slowest from neutron will be not less than 500 keV, like that, almost hundreds of keV. पर डिले न्यूट्रॉन का थोड़ा एनर्जी जो है वो थोड़ा कम होता है. क्यों? जो डॉटर का जो एक्साइटेशन एनर्जी है, that is less than the excitation energy of the uranium-236 itself. So the from neutrons energy, if it is average is 2 MeV, average is 2 MeV, here I have written, I make a 2 MeV, then the delayed neutrons average energy may be almost 1/4 of that. Okay, that's besides the point. Just as a data I am giving you. So अभी देखेंगे कि ये जो डिलेड न्यूट्रॉन जो है, so what is the significance of delayed neutron? ये तो आपको बता दिया था. The fraction of delayed neutron in uranium-235 fission process is 0.04% of the total number of neutrons emitted. अच्छा, ये देखो. The average number of neutrons emitted per fission of uranium-235 is 242. If I take all the pairs into consideration and take average of how many neutrons emitted per fission, almost 2.4, 2.42. This number is known as the reproduction constant, K we call that. If K is 1, that means this is instead of 2.42, if it is 1, then we call this critical operation. The reaction is self-sustained. This is achieved in a nuclear power generation reactor. Remember, these are the very important points to know. If K is less than 1, we call this subcritical operation. The reaction dies out. आप पूछे और पूछो आप, भाई क्यों चाहिए हमें reaction? So sometimes we require the reaction to die out. Why? Suppose I have to take the power plant into shutdown, because annual shutdown is a mandatory process. No, nobody on the earth can bypass that mandatory. That are mandatory requirement. So then if you have to shut down the nuclear reactor, then we have to willfully, by making the absorption of the neutron produced more by cadmium rods. So we bring it down the reproduction factor below 1. So that over a period of time, the nuclear power reactor can be shut down safely. अगर भाई ये देखो सबसे डेंजरस है, if K is more than 1, then in every fission more and more neutrons will be produced, and it suddenly leads to the explosion of energy generation, where it is used in nuclear bombs for military purpose. So we understand that in nuclear power reactors, K must be kept very nearly equal to 1 continuously to avoid nuclear explosion. ये समझ में आ गई आपको? चलो आगे बढ़ते हैं. कंट्रीब्यूशन ऑफ डिलेड न्यूट्रॉन इन कंट्रोलिंग द रिप्रोडक्शन फैक्टर. अभी देखो प्रॉब्लम क्या होता है न्यूक्लियर रिएक्टर में. एक एग्जांपल देता हूं. द एवरेज टाइम ऑफ ए न्यूट्रॉन emitted in one fission, so from neutron after generate for fission to cause another fission. One neutron generated, and it will be made to cause another fission after slowing it down. That time will be known as time between fission generation, TBFG, time between fission generation. One fission takes place, from neutrons comes out, proceed to cause the next fission. This time gap is known as time between fission generation. TBFG is almost 1 millisecond, a typical value, 1 millisecond. And for a nuclear power plant, it is around K. Let us take K is 1.001. 1.001, quite close to 1. So after n such generations, n such fission generations, the reaction rate will be how much? The reaction rate after n generation will be K to the power n, 1.001 to the power n. Suppose I want to make the reaction rate double, then what should be n value? 1.001 to the power n. It should be equal to 2. Take ln of both sides and calculate n. You will get n is almost 700. So after 700 fission generation, the reaction rate doubles. So ये 700 जनरेशन के लिए कितना टाइम लगता है? एक जनरेशन के लिए कितना टाइम लगता है? TBFG is 1 मिलीसेकेंड, तो 700 के लिए TBFG into 700, 0.7 सेकेंड लगेगा to increase the reaction rate 2 times. 0.7 सेकेंड is not a very large time. So इसे हम अगर 1.001 मेंटेन करते चले गए तो every 0.7 सेकेंड में रिएक्शन रेट डबल हो जाएगा. तो आप उसको कंट्रोल करना चाहिए, नहीं तो एक्सप्लोजन हो जाएगा. ठीक है ना? तो विद इन 0.7 सेकेंड के अंदर आपको फिर कैडमियम रॉड को नीचे डालना. यू हैव टू ब्रिंग डाउन दी कैडमियम रॉड मोर इनटू द फ्यूल. इज इट पॉसिबल? 0.7 सेकेंड में कोई ऑपरेटर कर सकता है ये? वेरी डिफिकल्ट, वेरी डिफिकल्ट. मैकेनिकल कंट्रोल तो ऑलमोस्ट नियर इम्पॉसिबल है. अंडरस्टूड दिस? ब्रिंगिंग डाउन द रिएक्शन रेट बाय मैकेनिकल कंट्रोल. मैकेनिकल कैसा होता है? हम कैडमियम रॉड जो कि न्यूट्रॉन ऑब्जर्वर है, वेरी गुड न्यूट्रॉन ऑब्जर्वर, उसको हम मोर डीपर इनटू फ्यूल में डालते हैं. वी lower the cadmium rod deeper into the fuel, but ये मैकेनिकल है, टाइम लगता 0.7 सेकंड कुछ भी नहीं है मैकेनिकल एक्टिविटी के लिए. सो यू कैनॉट कंट्रोल द रिएक्शन रेट if only you are depending on the prompt neutrons. अगर सिमिलरली के अगर 0.0999 है नियर 1 बट स्लाइटली लेस देन 1, द रिएक्शन रेट विल बिकम हाफ इन 0.7 सेकेंड। आपका रिएक्टर बंद हो जाएगा भाई 2-3 सेकेंड के बाद, ठीक है ना। तो या फिर क्या करेंगे आप, कैडमियम रॉड को थोड़ा ऊपर उठा देंगे तो फिर क्या बढ़ जाएगा मोर देन 1, फिर नीचे करना पड़ेगा। पर ये तो आप कर नहीं सकते, इतना फास्ट तो कर नहीं सकते। 0.7 सेकेंड ड्यूरेशन में आपको करना बहुत ही मुश्किल हो जाएगा, ठीक है ना। मुश्किल क्या है, इम्पॉसिबल है, बिकॉज मैकेनिकल सिस्टम हैव देयर ओन inertia. So to hold the value of k near to 1 by mechanical control is not possible. ये जो मैं एग्जाम्पल दिया उस आप कन्विंस हो गए होंगे अभी तक कि भाई मैकेनिकल कंट्रोल तो बिल्कुल बिल्कुल ही पॉसिबल नहीं है अगर फास्ट न्यूट्रॉन अगर प्रॉम्प्ट न्यूट्रॉन के ऊपर हम कंप्लीटली डिपेंडेंट है। तो व्हाट इज गॉडसेंड हियर, द गॉडसेंड इज a delayed neutron. How does it help? I have discussed about that in the fission of uranium-235. 0.64% neutrons are delayed. They are delayed neutrons. 99.36% neutrons are from neutrons. है ना। तो as seen in the above, that the मैंने आपको बताया अभी जो TBFG time between fission generation is 0.1 second. That means the average lifetime for a prompt neutron in causing fission is 1 millisecond. 1 millisecond में TBFG. Okay. So it is also calculated delayed neutrons are delayed by 14 seconds on an average. I've given that information earlier also for uranium-235. So what is the average TBFG taking prompt and delayed neutron both? 99.363% having time span of 10 to the power minus 3 seconds and 0.64% of the total neutron having time span of 14 seconds. So that gives us 0.091. Okay, this is the average TBFG. हो गया ये, समझ में आ गई। So therefore the time to double the reaction rate कितना 700 चाहिए ना मेरे को, with k is 1.001. ये लिख देता हूं, with k equal to 1.001 है ना। तो कितना टाइम लगेगा टू डबल द रिएक्शन रेट, 700 into 0.091, 64 सेकेंड। सो 64 सेकेंड में डबल होता है, और 64 सेकेंड इज क्वाइट ए बिग टाइम compared to 0.7 second to lower the cadmium rod or to lift the cadmium rod to adjust the K value to keep it almost near 1. So mechanical control the reaction becomes possible. Without delayed neutron, as you have seen already in this example, the mechanical control is simply impossible. Of the reaction rate, mechanical control of the reaction rate is simply impossible without delayed neutrons. ठीक है। तो ये आपको मैंने आज एक बहुत इंपॉर्टेंट इंफॉर्मेशन दिया, आपको भी समझ में आ गया कि जो हमारा जो न्यूक्लियर पावर स्टेशन है एक्चुअली इन डिटेल हाउ काम करता कैसे। तो आप सब जानते हैं कि चेन रिएक्शन होता, फिर हम लोग के मेंटेन करते हैं, वन बाई कैसे मेंटेन करते हैं, ठीक है ना। ये डिटेल हमने आपको बताया। एक नोट लिखता हूँ, द एक्साइटेशन विद डिलेड न्यूट्रॉन एमिटर न्यूक्लियस दैट इज डॉटर स्टार्टर इज मच स्मॉलर देन द एक्साइटेशन एनर्जी ऑफ डायरेक्ट फिशन फ्रैगमेंट। जब फिशन के बाद जो प्रोड्यूस होता है जो एक्साइटेशन एनर्जी यूरेनियम-235 का, ये बहुत ज्यादा होता है कंपेयर टू एक्साइटेशन एनर्जी ऑफ द daughter nucleus which produces delayed neutron. Therefore, the average energy of the delayed neutron is also smaller, almost 1/4 of the average energy of a prom neutron. So the delayed neutron, अगर average energy of prom neutron is 2 MeV, ये 500 MeV तक around रहता है. किसका delayed neutron? So 500 keV तक रहता, not 5 MeV. 2 MeV is the first the prom neutron. So delayed neutron का average KU will be around 500 keV or 0.5 MeV. So the delayed neutrons are more efficient in causing further fission. आप पूछो क्यों? भाई ये तो स्लो है, ऑब्जर्व हो जाना चाहिए. नहीं, in a fuel, even if a enriched fuel also, the uranium 235%, in enriched uranium will not be more than 3.5 to 4%. Remaining one will be mostly uranium 235, uranium 238. पर uranium 238 का खासियत ये है कि वो फास्ट न्यूट्रॉन को थोड़ा इजीली ऑब्जर्व कर लेता है कंपेयर टू स्लो न्यूट्रॉन. So the prompt neutrons has a more likelihood of getting absorbed by the uranium 238, which is present in the fuel. You can't just remove it because it is quite abundant in nature. In the fuel, it is more abundant, much more abundant than uranium 235. So during the moderation process, this uranium 238 tends to absorb some fast neutrons, but the probability of observing the from neutrons becomes more, but the probability of observing the delayed neutron will be less because delayed neutrons are having less kinetic energy. So on an average slower than the from neutron. So they will be causing further fission. The delayed neutrons have a good role, is a big role of course, in causing further fission. Okay, during the moderation. ये भी आप ध्यान में रखो. But the most important point is this: increasing the TBF, time between fission generation. This is the role of the delayed neutron, critical role of the delayed neutron, which enables us to mechanically control the reaction rate, keeping the regeneration, keeping the K value. This is the reproduction constant K value near 1 we have to make. Okay? The subcritical and critical, supercritical are no issues. We don't care about K is how much greater than 1. But critical operation, which is for peaceful purpose or clean power generation, we have to be very particular about K value to be maintained constantly around 1. Okay? And for that purpose, delayed neutrons are godsend to us. Without delayed neutron, we have to forget about the nuclear power generation. I think I have made myself clear. I think I have tried to explain it as simply as possible. I'll be go through my lecture again and again. You will get a feel of it and just clarify and your knowledge, boost up your confidence, and all my best wishes for your ongoing exams and also upcoming exams. All the best. We'll meet again continuously from now on. We'll continuously meet and we discuss very important points in all topics of our syllabus, our IIT, JEE, NEET syllabus, whatever the critical points I'll be discussing with you. Please come to my channel more and more frequently. Subscribe if you are not yet, so that you'll get update when I am sending new videos. Okay, thank you all. Have a good day.